First of all, it's a pleasure to be here. I want to thank the organisers for inviting me. It's been a fantastic symposium. We're nearly halfway through. We've had 2 half days. Tomorrow we have another day. It's going to be great. What we've been hearing about the last few hours is we've been hearing about very small things from Barry and a lot of small carvings. Now I'm going to talk about big things, big buildings. Why can't we do big things in wood? And you'll hear here, I've got a lot of pictures, only pictures, few words, and let's see how we go. I want to start by talking about earthquakes, because here in Turkey we have an earthquake-prone country, and where I come from in New Zealand, 4 years ago, 2011, we had a big earthquake. It was really scary. But among other things, this is what tended to happen in the earthquake. You can see this old building here, the old masonry building. All the stones and bricks fell down, but the wooden part, it stayed up. This is my office after the earthquake. So this kind of shaking that took place, everything is thrown about. Of course, my office is easily fixed up. That's not such a big problem. But other buildings were like this. And that building in the background there, when the earthquake happened, I was inside this building, and I just was walking to try and find my family. I tried to go here to help. This guy says, no, no, you don't, move on, because people were killed in some of these buildings, and it's a very important thing. So when we talk about tall wood buildings, we have to think about earthquakes. Some people were killed in our buildings, about not so many, 180 people, but I'm not here to talk too much about that. If we look at timber buildings and the earthquakes, most of them got moved like this. This little building here, it used to be 3-story apartment building before the earthquake. After the earthquake, only 2 stories, because it came down 1 story, because of not enough bracing in the building. And now, in my city of Christchurch, about half of the city has been taken down. We have a lot of rubble everywhere because the buildings were damaged. And so the question now in my city is, what about rebuilding the city? What kind of city do we want? Everybody is asking questions about a green city, sustainable, about transport, about bicycles, about community heating, all these things. And one of the questions we're asking is, what about a wood city? Why not wood, to rebuild the city in wood? Well, of course, it won't all be wood, but it could be. And you might say, why not wood? Well, we've done it before. This is a big building. It doesn't look like a wood building, but it is. It's a wood building in Wellington, our capital city. It was built in 1876, 150 years ago. And why was it made in wood? Because of earthquakes. So, just a few words. If we want to, some people would say, why use wood? Well, there are lots of reasons. Because it's fast, and it doesn't cost any more, and we're using a renewable resource from our renewable forests, and it's carbon neutral or carbon negative because we're storing carbon in the wood materials for hundreds of years. It's lightweight. We save on the appearance, we save on the foundations. It's a lovely appearance. It's got excellent performance in fires or earthquakes. So lots of good reasons for building in wood. But then on the other side, you would say, a lot of people would say, but. There's lots of reasons for not building in wood, because we have a very conservative building industry. And we have a very strong lobby from the steel industry, the concrete industry. They don't want us to take their business. And the designers, they don't know how to design tall timber buildings, and the architects are unfamiliar with the material. And there's lots of perceptions about the obvious things, about what about fire safety, what about durability, what about noise between one room and the next, what about the thermal insulation. All of these things have to be considered. So it's not a simple question, it's big questions. And then the question is, what about materials? Well, we have wood materials, but I'm going to mention 3 particular materials. We have what we call glued laminated timber, where we take small bits of wood and we glue it together into big beams. And we have a new product we call LVL, laminated veneer lumber, where we peel into thin layers like plywood, but we glue it back together into huge pieces of wood like this This is what we mostly use in our research because these people fund our research. But there's a new product now. It's called CLT. What is CLT? Cross-laminated timber. It's like taking timber and making very thick plywood and making very big panels, and I'll show you some of this stuff. So those are the materials. And then for the structural engineers, and I know you're not structural engineers or architects, but we have a lot of questions about what kind of structural system do we use? Are we going to have traditional post and beam, or the light timber frame, the Americans called 2x4 construction, or do we use the glue lamp or the cross lamp, or at the bottom of the list I'm going to tell you about something special we call press lamp. It's a new system. I'll tell you in a few minutes. But let's look at the old systems. So where's this? I took this photo yesterday at lunchtime. So here we have a tradition here, traditional post and beam with wood and masonry infill. This photo I took this morning when I was jogging down here. And you can see here, this is, when you look at an old building, you have to see the very old buildings to see the structure. But what you have here is you have wood. And you have cross bracing here. This cross bracing is very strong to hold the building up against earthquakes. On this side, we have no cross bracing. So that's a very important part. And then I went around the corner and I found a new building. This is taken this morning, just down here, just near our... And so this new building, I went inside. I had a look inside the building there. I had a cup of tea with the security guard. He was very nice. And if you look in there, you can see it's like this. So they have a lot of cross bracing here, and then they put the brick inside, and then they put the facade. So very nice construction, very good construction. This is good for house construction. But if you want to build a building that's 5 stories or 10 stories, can you use this? No, we have to do something better than that. We have what we call the light frame construction, 2x4 construction, which is very common in North America and the UK and in New Zealand. And you can build buildings like this, 4, 5, 6-story buildings, no problem. But you have to have a lot of walls. Then we can go to glue laminated, and you can go bigger than this. This is in Austria. This is a model of a building designed by Hermann Kaufmann, and that's the actual building being built. And when I went to visit it, that's inside the building. So this is a mixed construction, concrete and wood combined. But this is happening now in Austria, in Switzerland, in Zurich. This is a very famous architect, Shigeru Ban, a famous Japanese architect. He's designed that building that's under construction. This is another building in Zurich, 7 stories building. So this is happening using this glued laminated timber. In Germany, here's another building about the same size. And this building I went to visit because my son lives in Berlin. And I went to visit this building, and now it's completed. Nobody knows it's a timber building, but during construction, this is what it was like during construction, because it's mixed wood and concrete, and underneath it's like that. So I want to have a look, just talk about this wood here, this wood ceiling. What's that wood doing? Well, first of all, it's providing some boxing to hold the concrete in place, but it's providing reinforcing for the concrete. What else it's doing? It's providing fire resistance for the concrete because it burns so slowly. And finally, it's the finished ceiling. It will be there forever in the building. It's finished. So we can combine materials like that. It's very nice. In Canada, the Canadians are very good at this. They have some beautiful buildings. This is on the campus at UBC, where I was a student many years ago. This is the new Geological Sciences building with diagonal braces. So this diagonal braces, just the same thing I saw down here in Eskisha here to hold the building up. And then they have these beautiful stairways, beautiful buildings. This is another building on the UBC campus with glue lamp. Exciting, really exciting stuff going on. So this is another building in Canada, in Quebec. This is a very expensive building from the pharmaceutical company. Inside it's beautiful like that. So we have all these options. I mentioned before the CLT, cross-laminated timber, where you make big panels. And in London now, we have this building is 9 stories. There's more than one in London. And when you see the finished building, it doesn't look like wood, but the entire building is made like this with wood panels which were prefabricated in Austria, and every week a truckload of wood came from Austria, and they've made another floor, so 9 stories made in 9 weeks. Incredible stuff. And the same in Australia now. This is the tallest one. It's half finished there, but this is now 10 stories built in Australia. But these are in areas where there are no earthquakes. If we're going to be concerned about earthquake areas, we have our press lamp system. Now, I'm going to stop and move to the front a little bit because I have my toy. Everybody has toys today. We had toys before. This is my toy. You see my toy here? It's one of these toys you can buy in a shop for the kids. But my question is this: why not make buildings like this? Why don't we make buildings so when we have a big earthquake or a cyclone or a hurricane, the building moves a bit, it absorbs some energy, and then it snaps back again? Why not try that? Okay. So we have tried this. In New Zealand, we call it press lamp. Press lamp is pre-stressed, laminated, and I'm going to tell you about it. So, and the idea is not a new idea. The idea came from the concrete industry. This is University of California in San Diego with precast concrete. They had the idea, and my colleagues in my university, I had some Italians, they came from California, multinational, and they said, oh, this wood you have, this LVL, it's very strong. Why don't we try this rocking system with wood? So we tried it, and it worked very nicely. Because if you're going to make a prefabricated wooden system, it's easy to make it like this, with a hole in the middle, to put through the rubber band. Except it's not rubber band, it's high-strength steel. You can do it like this. And so the system is kind of like this. Suppose we wanted to make a 3-story building. We could stand up the columns, we could drop in the beams like that, and how do we join them together? We just run a tendon through, high-strength steel, and we anchor it there. And what that does, that we call it post-tensioning or pre-stressing. And that post-tensioning makes the connection between the beams and the columns. It's very simple. We can do at the next level the same, and we can put it through like that. So this is the idea that came from the concrete industry. We tried it with wood. If we want, we can put some diagonals. I talked about this before, to make it even stiffer. Or we could do it with walls, and we could put the tendons in vertically, like this, vertically, and we can bring in some other steel brackets for earthquake resistance. And we tested many of these in our lab, many of these. If you look at the date, 2006, long before we had the earthquake, our first testing, 10 years ago. And we get this very nice hysteretic behavior I won't talk about. And then we built a building in our lab like this, a kind of 2/3 scale building. And you can't see it, but we have frames and walls, and the red line is where is the rubber band or the high-strength steel, inside there or there. And then these people came and stressed the building up, and we did many tests on that, 20 or 30 earthquakes with no damage. And then we took it down and we built it again as a real building, and we put the tendons back in, and the building is finished. And that building was up like that when we had our earthquake in 2011, no damage. And where's the building now? It's gone again. It got taken down, it got sold to a lawyer in the downtown. He's going to make his office in that building. This is sustainability. This building is being already used for the 3rd time. And let's look at some buildings in New Zealand now. This was the first building, a building like that with big walls and tendons inside, and this is the design engineer with the anchorage. So big polytechnic building. This is another building, a university in Wellington, looked like that. And this is the high-strength steel that runs through the building, and it's stressed up with a hydraulic jack, and you can see the tendons here, and it ties the whole building together. We're just taking ideas from the concrete industry, like pre-stressed concrete, but we're using it in wood. Now in Christchurch, this is the architect's drawing. Let's make a new building like this. Then the engineer makes a drawing. This is the engineer's drawing like that. You can see those kind of H frames. And then this is the building being constructed, going up, and then this is the building nearly finished, and you can see here, you can't see the tendon, it's hidden inside, but you can see the anchorage here. So hidden in there is the tendon. And then the building is, now it's nearly finished, it looks nice on the outside. So we're just using wood instead of concrete or steel for buildings like this. This is another one, it's half finished now. This building has no concrete in it. It's in a small city centre. There will be a museum on the bottom floor and a library in the middle and all the city offices on the top story. And this is the last one I'll show in Christchurch. We call this hybrid because it's mixed materials. The columns are concrete, the beams are wood, and it's all post-tensioned in both directions, just like I showed you. So this one is almost finished. And this is a very poor photograph because I just tried to grab this now. It's a very new photograph. But this is in Zurich, at ETH in Zurich. And this building is just be opened very soon because it's the first one in Europe. So then the question is, well, how high can we go? Everybody will ask, how high can we go with these buildings? Well, these two buildings are happening now. In Norway, this one is 17 stories. It's under construction. It's happening. This building here in Canada, the Canadian government had a big prize. They said, we have putting up $5 million of prize money, anybody who can make a timber building more than 10 stories. And there are actually 3 winners of that. One in Ottawa, one in Vancouver, one in Quebec City. This one in Ottawa I know about because we're helping the designer from New Zealand. We're helping the Australian designer who lives in Quebec City to make this building that's coming. And then if we look to the future, these buildings are just ideas. They're not real buildings, they're just ideas. But in Austria, the Austrians have just announced last week they're going to build this building 24 stories. In Canada, there's Michael Green is the architect in Canada who wants to go 30 stories. Actually, if you want to know about this kind of stuff, Michael Green is a fantastic architect and he has a beautiful YouTube video which talks about using wood instead of concrete. And in the United States, in Chicago, the Skidmore, Owings and Merrill, they want to go 42 stories in Chicago. Is it possible? Of course it is possible. Will it happen? Maybe not. This is not the market. But the point here is that we can go anywhere. So my last slide is simply to say my conclusions are very general. I'd say this. What we need is we need more forests, we need more trees, we need more wood, and we need more timber buildings. And if we do that, this will be good for our health and our wealth and a sustainable planet. Thank you very much.